Hi everyone, welcome back. Hope you are doing good. This is Mahesh. In this video, we will continue on examples of computing time complexity. So in the earlier few videos, we have seen how to compute this time complexity for the iterative algorithms. In this video, we will start with the recursive algorithms. So basically, what is this recursive function or a recursive algorithm? So basically, it is a function that calls itself. It is a function that calls itself. So why there is a need to call for a function itself? So normally this is used in divide and conquer technique. Okay, so for certain problems, what we do, if the problem is bigger and if it can be divided into a small problem, and if we can solve the smaller problem and then we can combine together to get the solution for the bigger problem, that time, we will try to use divide and conquer technique. Okay, so that is where we will use this recursive algorithms. So we will look into this divide and conquer technique maybe later in the upcoming videos. Maybe we can see that in merge sort, and also there are so many algorithms where we can use this divide and conquer technique. So, but here our main motto is to look into the time complexity of this particular recursive algorithms. So for that, let us consider one or two examples or few examples so that we get acquainted with how to compute the time complexity for these recursive functions. Okay, so now if we consider recursive functions, there can be two recursive functions. Okay, so one is decreasing function and another one is dividing function. So what exactly this decreasing function does? So it will solve some problem, then it gets decremented. It does not get divided, it gets decremented. What I mean is, so assume there are n items. Okay, then I will solve for one item, then I will call my function again for n minus 1 items. So here the problem statement is getting reduced, it is not getting divided. But when it comes to dividing function, here what happens, the problem gets reduced by half or 1/4 or something like that. So basically the problem gets divided. So let us assume there is a function of n, there are some n items, and what we do, we will divide them half, n by 2 and n by 2. Again this gets divided by 2, so we will solve n by 4, n by 4, and again this will be like n by 4, n by 4. So this is how the dividing function tries to solve the bigger problem by dividing the bigger problem into smaller problems, mostly half first and the next half in the next iteration, something like that. So we will have decreasing function and dividing functions. So first let us look into some examples on decreasing functions. Okay, so this is our first example for recursive function. Now if you see here, we have a main function with n inputs. Then what it does, it will check whether n is greater than 1. If that is the case, then what it will do, it will return, or it will call itself with a decreased amount of inputs. So maybe n minus 1 here in this example. So how to write the time function for this example? So that's the first thing we have to learn. So if you see here, this is our function fn. So assume t of n is the time function that we want to compute for f of n. Okay, so now what happens, here there is a condition check, so which takes 1 unit of time. Okay, now what it does, it will call function n minus 1. So if Tn is the time function for f of, the function n, then for function n minus 1, it will be t minus 1. We can say it is t n minus 1, sorry, t n minus 1. So if that is the case, then what is the total function Tn for this equation? It will be 1 plus Tn minus 1. But this is when n is greater than 1. This is when n is greater than 1. As soon n becomes 1, then this problem is solved. There is only condition check that happens. So maybe it will be only 1 when n is equal to 1. Okay. So this is the time function for this particular recursive algorithm or recursive function. Now with this function, I want to compute the time complexity for this particular algorithm. So how to do that? Now we have this time function. There are two ways. Using this time function, we can compute the time complexity for this algorithm. So what are those two? The first one is back substitution method, and second one is recursive tree method. So we will look into both the ways for this particular example. Now let us see how our back substitution method works. So we have Tn equal to 1 plus Tn minus 1. Maybe for easiness, what I will do, I will write it as Tn minus 1 plus 1. Okay. So what exactly is back substitution? So if we know, to solve t of n, we should know Tn minus 1. That is correct. But we don't know Tn minus 1. So what we need to do, we need to try to figure out the value of Tn minus 1. So how do we do? So let us assume we have this equation which is 1. Now on the right side, what I will do, I will try to compute Tn minus 1. So if it should be Tn minus 1, then wherever n is there, then I should replace it with n minus 1 here in this equation. So I'll do that. So t, instead of n, what I will do, I will say n minus 1, then minus 1, then plus 1. So my t of n minus 1 will be t of n minus 2 plus 1. Okay, this is my second equation. Now what I will do, I'll substitute equation 2 in my equation 1. Okay, so now t of n will be, so here I will replace this t of n minus 1 with this particular value. So what I will do, I will take Tn minus 2 plus 1, okay, then plus 1. If I simplify this, it becomes t of n minus 2 plus 2. Okay, so this is my third equation. Now again, to calculate t of n, we need the value of Tn minus 2. So we don't know what is Tn minus 2. Again, what we will do, we will try to figure out the value of t of n minus 2. Then it becomes t of n minus 2 minus 1 plus 1. So I am replacing the value of n with n minus 2 in this first equation. So if that is the case, this becomes t of n minus 3 plus 1. This is my fourth equation. This is my fourth equation. Now what I will do, I will substitute fourth equation substitute 4 in 3, not 1. Okay, so T of n becomes T of n minus 2 is this much, T of n minus 3 plus 1, then plus 2, the remaining term. Now if I try to solve this one, my T of n will be T of n minus 3 plus 3. Okay, so how long should I do? There is no need to do further, because if you observe, when n it is Tn minus 1, when it is n minus 2, it is n minus 2 plus 1. When we keep on substituting this, we are getting a kind of pattern here. So initially it was T of n minus 2 plus 2, correct? Now it is T of n minus 3 plus 3. So how long it continues? Maybe to some value, say for example k. So T of n equal to T of n minus k plus k. Once it reaches here, maybe it stops. So now what we need the value of n minus k. So one thing what we can observe from this algorithm, so our loop stops, or this execution almost stops when n becomes 1. So that's a base condition we have. Okay, so therefore our loop stops when n becomes 1. So we will use this one. If that is the case, then to reduce it to 1, our n minus k should be 1. Correct, right? If that is the case, n becomes k plus 1. N becomes k plus 1. Now what I will do, I will substitute this n value here in this example. So Tn equal to T, what is n? It is k plus 1 minus k. And what is the value of k? I mean, if I try to simplify this one, k will be 1 plus n. So we got both the values. Now it will be 1 plus n. Why I am trying to substitute the value of n here? Because I know the base condition. Base condition is nothing but our T of 1. So when our n is 1, we know that this will be 1. So I want to reduce it to get this particular base condition, which is T of 1. So now if you see, this gets cancelled, it becomes T of 1 plus 1 plus n. Correct, right? Now this T of 1 is nothing but our value 1 plus 1 plus n. So that is nothing but n plus 2. So if that is the case, then our order becomes O of n for this particular algorithm. So this is how we use this back substitution method, and we try to get the order of a particular algorithm. Okay, so this is using back substitution method. So what we do, we try to figure out how a particular time function can be generalized. So generalized in the sense it should be expressed in terms of n and k. Then finally, I mean, we will substitute n and k values to get the final order of the particular algorithm. So this is using back substitution method. Now there is one more method we understood, right? I mean, there is a recursive tree method. So what is this recursive tree? So let us try to understand that. So in recursive tree method, so in this one, let us try to understand this function. What it does, it will check whether n is greater than 1. then what it will do? It will call again the same function with n minus 1. When it is n minus 1, again it will check if that particular n minus 1 is greater than 1, again it will call n minus 2. So this continues, right, unless this value, the n value, becomes 1. So let us try to represent that in the recursive tree. So initially our function will be with n inputs. Then what it does? It will do one check and then it will call function n minus 1. Okay. Next, again it will do one check and then it will call function n minus 2. Again the same, it will do one check, then it will call function n minus 3. How long it will happen? It will happen until this reaches 1. So once it reaches 1, basically function 1, that is n minus 1, which is nothing but function 1, then it stops because it reached the base condition. So now if you see here, from 1 till the value of n, it executes, right? So it means how many executions happen, and in each execution there will be only one check here. There will be only one check, there will be only one check. So that's a single unit of work. And if you see, the n iterations will happen. That's why we can say it is of order n. So this is how we can use the recursive tree method to figure out the time complexity for this particular recursive functions. Okay, let us look into one more example now. This is our second example. So in this one we have function n, and if n is greater than 1, then it does something, and after that it will call function n minus 1. So if for function n, if t of n is our time function, then for this one it will take order of 1 unit of time. And then if you see, this is a for statement, right? I mean, it will execute from 0 until n until I becomes n. So it means it executes for n times. Okay, then it will call function n minus 1. So it means if tn is the time function for function n, then for function n minus 1 it can be t of n minus 1. Okay, so if that is the case, then what is total tn? Our total tn will be t of n minus 1 plus n plus 1. So this is the time function. This is when n is greater than 1, but it becomes 1 when n is equal to 1. So this is our time function for this particular algorithm. Now using this, we will try to come up with the order of this particular algorithm. So now we will do that using both the method, one using back substitution and another one is the recursive tree method. First we will start with the back substitution. So let us take tn equal to t of n minus 1 plus n. So we will ignore 1 for now. I mean, that's how it becomes simpler for us to figure out the order if we have only equation in terms of n and t of n. So now let us call this equation 1. Okay, now what we can do, we can compute tn if we know t of n minus 1. So how to compute tn minus 1? Let us see. Tn minus 1 will be, so wherever, so we will substitute n minus 1 wherever we have n in our equation 1. So if we do that, then what we will get, t of n minus 1 plus n, that is equal to t of n minus 2, sorry, this will be minus 1 because this is n, so this will be n minus 1. Okay, so let's call this equation as 2. Now let's substitute 2 in 1. So if we do that, our Tn becomes t of n minus 2 plus n minus 1, then we have this n here, so that n. Now we will call this as equation 3. Now again we have this Tn minus 2, so let's try to figure out what is Tn minus 2. That will be t of n minus 2 minus 1 plus n minus 2. This will be t of n minus 3 plus n minus 2. Let's substitute. Let's call this equation 4 and let's substitute this in equation 3. Then our Tn becomes t of n minus 3 plus n minus 2 plus n minus 1 plus n. If we somehow simplify this, it becomes t of n minus 3 plus 3n and then minus 1 minus 2 minus 1 will be minus 3. So this is our simplified equation. Now if we see and if we try to generalize this one, how we can generalize? Wherever we have this value 3, so now this is third iteration, maybe we have k iterations, so it becomes Tn equal to t of n minus k plus kn minus k. This is our fifth equation. So this is the generalized equation. Now our main motto to remove this t of something. So for that, what we know, the base condition or the condition where Tn equal to t of 1 equal to 1 when n equal to 1. So this one we know. So we will try to reduce this t of n minus k to this t of 1. So if that is the case, then our n minus k should be 1, correct, right? So if that is the case, then our n will be k plus 1. So we can use this. And also if there is, since we have k, we want to express k in terms of n, so our k will be 1 plus n. So we can utilize these two equations. Let's substitute them in equation 5. Then what happens? Our Tn will be t of, in place of n we will substitute k plus 1 minus ka, okay, then kn, k into n. So we will substitute the value of k here, 1 plus n into n minus k, so which will be 1 plus n. So let's try to solve this. This goes off. This will be t of 1 plus n square minus 1 minus n. So this gets cancelled. This is nothing but 1. So it will be 1 plus n square minus n. So this gets cancelled. So somewhere this will be n square. So this is of order n square. So this is how we get the order of this particular algorithm. This is using back substitution. Now let us see the recursive tree method. Okay, so in recursive tree method, let's try to understand what is happening. Initially we have f of n, correct, right? Now this f of n, in the sense it is nothing but function n. Now what it did a for loop of n iteration, and then what it did, it called f of n minus 1 or function n minus 1, correct, right? Now in the next iteration what happens? So again it will do n amount of work, but now it is not exactly n, it will be n minus 1 amount of work, and then it will call f of n minus 2, because when it calls f of n minus 1, here if we see this example, when this becomes f of n minus 1, here this n also will be updated with n minus 1. So it iterates from 0 to n minus 1. When this becomes n minus 3, again this iterates only from 0 to n minus 3. That's why on each iteration it gets reduced by 1. Now again it will do n minus 2 amount of work, and then it will call f of n minus 3, and so on. It continues till it becomes f of 1. Correct, right? And this will continue, and it also becomes somewhere 1. So whenever this becomes f of, if you see, it reached f of 1, so it stops here. So if you see, there are n steps or n iterations. Correct, right? And each iteration, what is happening? The amount of work done is getting increased. Initially it is 1, then 2, and so on. It goes up to n. Now if we want to get the total work done or the total time complexity, then what we have to do? We have to add up all of them. So till n minus 1 plus n. Okay. So this is sum of n natural numbers. So if we solve this divided by 2, so it becomes of order n square. Okay. So this is how, we compute the time complexity using our recursive tree method for such recursive algorithms. That's it for this video. Hope you liked the content. If it is the case, please consider subscribing my channel and also like the video and share it with your friends. Thanks.